Good afternoon, everyone. My name is Sophie Calderwood, and I will be talking to you today about optical flow tracking in solar flare ribbons. So to dive right in, I'm going to first talk to you about the motivation behind my study, despite it being my final year project and me having to do something. And then I'm going to go into a bit of the background, and then eventually into the analysis and to the algorithm that I developed and then the results that that eventually produced. So solar storms cause charged particles to be ejected from our sun. When these charged particles interact with our Earth's magnetic field, it can produce some stunning displays like our Aurora Borealis. However, it can cause some serious problems, especially with disrupting satellites, power grids, and communication systems. This isn't just a thing that happens on our star, though. It happens on a host of other stellar objects, giving us a broader understanding on solar and astrophysical processes on a wider scale. And since its launch, the IRIS telescope has produced over 24 million images. This level of data is overwhelming the solar physics community. Therefore, it's more crucial than ever to have reliable, automated analysis processes to continue our research. So our sun is an incredible laboratory in itself. However, I am going to be focusing on the chromosphere and the photosphere of the sun. You can think of this as the surface of the sun. So what is a solar flare? A solar flare is an impulsive release of radiative energy across a large range of the electromagnetic spectrum. It happens when the sun's magnetic fields twist and twist and twist until something called magnetic reconnection happens, which allows the magnetic fields the chance to reconfigure and release this great twist energy in the form of a solar flare or a coronal mass ejection. However, what the focus is today are the foot points of these flares. These are called solar flare ribbons. Visually, as you can see, they are bright strands seen on the chromosphere of the sun, and we believe that they are formed due to strong heating of chromospheric plasma, but how that energy is transported is still a very, very active area of research. The data from this project was taken from the Interface Region Imaging Spectrograph, or IRIS for short. Launched in 2013, the space-based observatory houses two instruments, a spectrograph and a slit-jaw imager. The latter is what my data is taken from. The slit-jaw imager works because light passes around the area, it passes through the slit and is reflected off an area. It passes through filters, then onto a CCD, which can be thought of as a camera, where our image is eventually produced. And sifting through the masses of data collated by the telescope, there were a couple specifications which made a viable flare candidate. The first was that it had to be of a medium to high energy. This corresponds to an M or an X class flare. It had to be of a high cadence, ideally 10 seconds. This is just the time between successive exposures. And it had to be of a slit-jaw imaging filter of 1,330 angstrom. This corresponds to a carbon-2 emission. And this is the flare that we ended up deciding on. So within a solar ribbon, there are lots of small-scale structures, and it's how these structures change over time that I will be tracking. I will be referring to these as blobs. So step number one is in a true wavelet transform. A wavelet transform breaks down a signal into localized oscillations. It works similarly to a Fourier transform, which breaks down a signal into frequency. Think of it as like a song with lots of different harmonies in it. And this does this by using infinite sines and cosines. A wavelet transform breaks down a signal into its frequency components, but also its time components. Within a song, you are told at what point the instruments come in, as well as what instruments are there. It's also a lot more flexible because you can use short-lived and non-periodic functions to stretch and compress to analyze the signal a wee bit better. Behind me is an image. This image of a cat shows a two-dimensional discrete wavelet transform. And by discrete, I just mean in little packets and chunks. The image is first passed through a low-pass filter and then a high-pass filter and is downsampled by 2. Wavelet transforms can be thought of as a microscope. You use a wide, low-resolution lens, you get the bigger picture. And then if you use a narrow, higher-resolution lens, you see the finer details. This image is then downsampled by 2, which is essentially halved, and then for a two-dimensional image, it's first repeated along the rows and then the columns. And this process can be iterated multiple times, which is called levels. What I used specifically was in a true wavelet transform, which is French for with holes. This wavelet transform works in the same way as the discrete counterpart, yet it is a stationary wavelet transform. It means that it does not downsample. It keeps the same resolution throughout all of the analysis, which is very ideal. And then choosing the right wavelet depends on what type of analysis you want to complete. I looked at the data, I saw it was non-negative and had quite a smooth gradient, so I thought a Gaussian was the best fit. Unfortunately for me, the pi-wavelet library I was using did not have a Gaussian a discrete Gaussian on hand. Therefore, I had to create my own. But applying this to our data, we get back this. This shows a level 7 decomposition, which is much more than is required, but for demonstrating the purposes of a true wavelet transform, I find it is quite effective. And after a bit of visual inspection, it was deemed that level 6 and level 7 really highlighted those small features, those blobs that I wanted to track. So with this reduced image, we move on to step number 2, which is a Scale-Invariant Feature Transform, or SIFT. This just identifies blobs as key points. It was after reading a paper on the detection of red blood cells in a tumour, I was actually inspired to look at SIFT. It detects and describes local features and is unchanging when it comes to scale and rotation transforms. The centre of these circles show the key point of interest. The size of the circle represents the scale of the feature being tracked. So the smaller the circle, the denser the texture over fewer pixels, and vice versa for a larger one. And the radial line shows the orientation of the feature. Thus, feeding our SIFT algorithm the wavelet image, we can see that it really only produces key interesting points in the areas that we desire, in the bright spots of the ribbon. So with these key points identified, we move then on to step number 3, which is sparse optical flow tracking. Optical flow tracking is the apparent motion between two frames. Mathematically, you can think of it as a two-dimensional vector field which shows motion. And it makes two assumptions. One, that the pixel intensities are constant between two frames, and 2, that the pixels in the same area follow similar paths of motion. With these assumptions in hand, we can then determine the position of a pixel after a small change in time. And after you crank the mathematical handle a bit, don't worry, I will not go into it, you come out with equation number 2 here. So the S are the image gradients, but what's important are the UV terms here. This is the unknown flow vector, and it is how you solve for this unknown flow that gives you your different types of optical flow tracking. The one I utilised was sparse optical flow tracking, or the Lucas-Canady method. This only processes a few pixels at a time. Thus, if we feed it the SIFT key points, they should just track the SIFT key points. So finally, we move on to our results. We bring it all together. And here we go. As you can see, the most of the cyan points are concentrated in the bright spots of the ribbon. Therefore, it is detecting and tracking our blobs in the correct areas, which is very exciting. However, if we plot the X and Y coordinate of the first detected key point over time, and after a bit of the back of the napkin calculation, I realized that a blob shouldn't be moving more than 4 to 5 pixels per frame. As you can see, at a couple points, it's jumped over 200. Despite this failing, it is in fact detecting a pattern, as you can see in this video here. So what's going wrong? That brings us on to our next steps. Where do we track from here? A next step is to test this algorithm against more flares, ideally ones a little less eruptive than ours and with no video cut at the end, because the more flares you test against, the more problems that come up. The more problems that come up, the more solutions could be found to solve these problems to have as generalized an algorithm as possible. And since each of these components have their own parameters, systematically going through and finding the most optimal combination for blob tracking is a very big next step. However, the biggest next step, as you saw on the previous graph, and as you can probably see from this video here, is the issue with indexing and storing the tracked key points. How do we keep the same index for the same point, even if it disappears or reappears or another one comes up next to it? Unfortunately, or maybe fortunately for me, this is the basis of PhDs, so it's a little beyond the scope of my 20-credit physics projects, but it is still a real issue facing machine tracking at the minute. But these techniques can be used in a multitude of different areas. True wavelet transforms are used in textile defect detection. We have our SIFT, which is used in plant disease detection, and you have optical flow tracking, which is used in robotics and machine vision, to name but a few of their uses. So in conclusion, I've shown you how you can bring together wavelets, SIFT, and optical flow tracking to take you on a journey through twisting magnetic loops, eruptive flares, and of course, blobs, lots of blobs. Thank you very much. Any questions?